In the last podcast, we saw how particles are arranged in solids, liquids, and gases, and we saw that in solids, particles are arranged tightly together, and in liquids, the particles are also arranged tightly together, but in a disordered fashion, no long-range order in those particles there. And in a gas, we saw that particles were spread out in no order at all, and we can't see on this diagram, but the particles are zipping around, not bonded to one another, and just moving freely. So just three examples of materials. Steel would be a solid example of a solid, and water, obviously, a liquid, and oxygen, a gas. What I want to look at today in particular is what happens when a material changes from one of these states to another. For example, solid ice can change to liquid water, and liquid water can change to gas steam. So what actually happens during these changes? What happens to the particles? How do they get from one state to another? Now, wax is a good example to look at when we're trying to see what happens to a substance when it changes its state. Wax is good because at room temperature it's a solid. We get solid candles. But at elevated temperatures, the wax quickly melts. If we light a candle, the candle will melt at some temperature or other above room temperature. At room temperature, which is around 20 to 25 Celsius, the wax will be a solid. So we can do an experiment to investigate this. And here's part of an experimental setup. We've actually done this experiment in class, and we can see the materials revealing themselves there. What we do is we take a small amount of wax, put it in a test tube, and we immerse it into a beaker of water. We heat the water and the wax melts. We want to see what happens to the temperature of the liquid wax as it cools down. Now, it sounds like a pretty simple question. It cools down, so the temperature must go down. But how does it cool down? How does the temperature change with time? Let's firstly imagine doing this experiment not with wax, but just with water. We heat the water up, and we allow it to cool down, and we record its temperature with time. Now, the difference between the wax and the water is that the water will cool down, but it will remain a liquid as it cools from, let's say, 70 or 80 Celsius down to room temperature. The water won't change its state. The wax will change its state. So if we imagine what will happen to water as we cool it down on a set of axes such as these, time and temperature, the water will start off at an elevated temperature here, and we will cool it down, and it will get cooler and cooler and cooler. And gradually, as it gets closer and closer to room temperature, the rate at which it cools down will slow down. And when it reaches room temperature, and this temperature here would be room temperature, right there, room temperature. Label that RT. But if we repeat the experiment with wax, wax behaves differently, because as wax cools down from a liquid, it solidifies, and at room temperature it's a solid. So we see a different cooling curve. Now, initially the wax cools down, but at some temperature it appears to slow down. Its rate of cooling slows down, may even stop cooling down for some time before the cooling starts again. And eventually, after some time, longer than my graph allows, it will again reach room temperature, somewhere over here. So This one is the wax, and the other one water. Big difference. The reason for the difference, it's to do with the phase change. The wax changes from a liquid to a solid. Now the melting point of wax is around about something like 50, 53 degrees. I'm just going to write that in there. 53 degrees here. And this flat area corresponds to the time at which the wax is changing back from a liquid into a solid. The particles are getting themselves organized, they're rearranging themselves, they're losing energy, they're slowing down, and they're grabbing hold, and they're forming bonds. And as they form these bonds, they become more stable, we can say, and they release energy. They actually release some of their bond energy. And that energy keeps the substance warm. It actually is turns into heat energy and maintains the temperature of the wax higher than if it hadn't changed its state. So the water doesn't change its state, the water doesn't form new bonds, the water doesn't release this bond energy, and as a result it cools down more quickly because it doesn't have any extra heat to keep it warm. The wax does form bonds, the wax does release this bond energy as it becomes more stable, and this extra energy keeps the wax warm. So the wax is going from a liquid state into a solid state. It's going from here to here, liquid into a solid state. And it's, as I said before, it's difficult to see what's going on a still image like this. But fortunately for us, there are available applets, small applications that allow us to visualize what's going on. And PHET interactive simulations of University of Colorado, available at this website, have produced many simulations, and one of them allows us to visualize what's going on as material changes its state. So here we can see we have a container, we have a thermometer up here recording temperature in Kelvin, and inside this container at the moment we have neon, which is a type of gas at room temperature. Now I can click this to change it to water, and we can see here we have water particles, Mickey Mouse particles. They look like Mickey Mouse heads. H2O, the little red dots are hydrogens, and there's 2 of them per particle, and the blue one is oxygen. Now at the moment all these particles are arranged together, they're connected, they're not free to go wherever they want, so this phase must be solid. But if I use the slider here to add heat, we can see the temperature going up, and we can see the particles starting to rearrange themselves and move a little more freely. Once we exceed a certain temperature, the particles become much more free to move around, and we can see some of the particles are bouncing around in the container. Some of the particles are still stuck together. If I continue to add more heat, we can see that more and more particles will be free to move wherever they want. I can remove the heat as well. Below the freezing point, the particles are all stuck together. They're still moving, but they are stuck in a rigid position, and this is a solid. Above the melting point, we can see the particles are free to move around, to change partners if you like. They are free to move around in a given space. And above the boiling point of water, particles will be going wherever they want to go. They're not restricted apart from by the volume that they're in. There's a lot more space between the particles. The names we use for the phase changes, some will be familiar to you, some may be less familiar. As we heat a solid, it will melt into a liquid. Melting is the phase change from solid to a liquid. As we heat a liquid and it turns into a gas, we say that it vaporizes. As we cool a vapor or a gas down into a liquid, we say that the vapor is condensing. It condenses into a liquid. And finally, as we cool a liquid back down into a solid, we say that the liquid has frozen, it freezes or solidifies.